So good morning or good afternoon, everyone, depending on where you are. And thank you for joining us on our webinar on prospects for carbon neutral maritime fuels production in Brazil. I am Lavinia Hollanda. I'm shipping consultant at Climate and Society Institute, and I will moderate today's presentation and debate. So our agenda includes, after this brief introduction, a 40-minute presentation on the main results so far of the Climate and Society Institute study on carbon neutral maritime fuels for shipping, which is being conducted by the research team at Synergia Lab. Can I ask you to please keep your microphones on mute, just to avoid background noise, please? So our presenters today are Alexandre Szklo, Associate Professor of the Energy Planning Program at the Engineering School of the Federal University of Rio de Janeiro, and Joana Portugal, Adjunct Professor in the same institution in the same program. Together with Professor Roberto Schaffer, they are coordinating the research team that is conducting the study and will show the results present here today in this webinar. So following their presentation, we will have a 10-minute session of comments on the study from Yirang Zhou, Associate Researcher at the International Council of Clean Transportation, ICCT, who has kindly agreed to contribute in this debate. So finally, we will have a 20-minute Q&A session, which I will moderate. And if you have questions to the team during the presentation, please use the chat and send them via the chat. And I will present them to the researchers during the Q&A session. This webinar is being recorded, and within a couple of days after the webinar, the participants will receive the link to the recording and a consolidation of the Q&A session. So if your question for time constraints is not answered, they will be addressed and answered by the researchers, and you will receive your answer later on. Just a second, I'll mute everybody. Okay. I would also like to acknowledge the participation in this webinar of the members of Brazil's structure that addresses IMO issues, including members of Brazil's permanent representation to IMO and of Brazil's permanent representation to international organizations in London, members of the Coordinating Commission for IMO Matters and from the Ministry of Foreign Affairs in Brasilia, and members of the Executive Secretariat for IMO Matters in Rio. On behalf of Climate and Society Institute, I thank all the participants in this webinar. So let's get to business and start our webinar. In accordance to the targets established in the initial strategy by the International Maritime Organization to reduce GHG emissions, Climate and Society Institute has commissioned a study conducted by Synergia COPPE to evaluate the possibility of producing marine fuels with neutral emissions in Brazil. The first phase of the study was presented in a webinar on April 21st and listed the 5 more suitable fuels to be developed within the short term to help achieve IMO targets. Now, in the second phase of the study, more in-depth assessment of these fuels will be presented. In today's webinar, Professors Alexandre Szklo and Joana Portugal will be presenting the partial results for the first and second phase of the Synergia and COPPE study to the international shipping community. These results this study will have a third phase, which is expected to be concluded by July this year. So with this, Alexandre, I turn to you. To our presenters, Alexandre and Joana, and the floor is yours, so I'll unmute you. Let's see. Well, I think you are unmuted. Just a second. Alexandre, can you hear me?
Yes, I can hear
Okay.
you. I want to show my screen. I'm sharing my screen.
Okay, wonderful.
Just to start. Host, okay. Let's see. Can you see it?
Not yet.
Yeah, I'm sharing it. Sharing screen. Oh, you disabled me to share my screen.
I did.
Yeah.
Okay.
You have to enable me, please.
Let's see how I can do that. Okay. More.
So just to acknowledge, I'm facing some difficulties with the quality of my internet. Therefore, if you don't mind, I will turn off the video during my presentation, and then I will turn on during the questions.
Okay. So I can't find where I allow you to share the screen, but
Hi, Lavina, is Joanna here. To allow us to share the screen, you have to upgrade Alexandre and myself as co-hosts of the meeting.
Well, see if, Alexandre, see if it works now.
Yeah, it works.
Yes, it does. Thank you.
Okay. Okay. So let's do it. Thank you.
Can you see it? No?
Yes. If you can put it, yeah. Okay.
Okay, fantastic. So good morning for those in Brazil, and good afternoon for those in other time zones. I'd like to thank iCS for organizing this webinar and all of you that are here to participate and collaborate, particularly Johanna Rangzu from the ICCT and my research team from the Synergia Lab. I am Alexandre Szklo, as Lavinia said, and I will present the first part of this webinar. Then I will give the room for a much bright and nice presenter, which is my colleague, Johanna. I'm a professor in the energy planning program of the School of Engineering, the Federal University of Rio de Janeiro since 2003. This is the largest federal university of Brazil and the largest engineering school of Latin America. Again, I'd like to thank my colleagues in COPPE and the fantastic young research team of this project. Some of them finished their PhD now in the Netherlands, the case of Franciel and Eduardo. And some are at the beginning, some are in the middle of their master's dissertation, but all of them dedicate their minds to advanced fuels or shipping modeling, including the introduction of bunker into integrated assessment models into our integrated assessment models. So this project is part of a much broader research that is being done in our lab. This is the project supported by iCS and carefully coordinated by Lavinia. Thank you, Lavinia, for this coordination. It started December 2019 to be finished in the next month, I think July or mostly in August. It has 3 stages, 2 of them already completed, which will be the focus of this presentation. Actually, I made a long webinar dedicated to the first stage of the project in April, where I shown the details, the indicators and the multi-criteria analysis that supported the selection of alternative bunker focusing on the Brazilian deep sea shipping case. Here, I will not repeat it in details, but summarize its main findings, leaving time for the second stage of the project that has just come out of the oven. A final note here, the third stage that we already started will be based on our integrated assessment models, and by that we'll be able to account for indirect impacts of biofuels and e-fuels production on the whole energy and land use systems in Brazil, including impacts on water consumption and indirect emissions from land use change. That is the virtue of the integrated assessment models, integrated assessment tools. And we are going to use in the third stage our internationally recognized models. Therefore, in the first and the second stage of this project that we are going to present now, we are not assess the indirect impacts of biofuels, because this can only be done by land use models, and we will do that in the next stage of our project. That's our agenda. As I said, I will give the floor to Johanna in the middle of it, in the part 2. And let's start. That's my photo, and you can see me. I'm turn off the video, but that's me. As you know, IMO proposed a relatively draconian target for curbing GHG emissions of international shipping. Draconian because it's based on intensity, but more important than that, on absolute and on targets, on level targets. And for the latter, compared to the emission level of 2008. So this is particularly challenging for the case of Brazil. This is particularly challenging target for Brazil, given the pattern of the country's trade based on low value-added goods, non-refined minerals, and agricultural commodities. We have other studies in COPPE detailing this, the competitiveness of Brazil's trade, if bunker was carbon taxed, or and the carbon intensity of Brazil's major shipping trade routes. Worse than that, a significant fraction of Brazil trades goes to China, iron, crude, soybeans, and a smaller but still relevant fraction goes to Middle East countries, India, EU, European Union, and Russia. In sum, we are talking about low value-added goods at long transportation distance with few recurring rents because of quality. There is no major quality. The crude oil of Brazil is good, the iron in Brazil is good, but they are basic commodities. There are no major recurring rents related to them. And there are strong discounts because of distance, strong differential prices because of freight when compared to our competitors. For example, in the case of iron ore, we are competing with Australia for the Chinese market. In the case of crude oil, we are mostly competing with USA and Saudi Arabia, Iraq, to provide crude oil to China, mostly China. So we are in a difficult situation because of that. Still, Brazil may have some competitive advantage when we evaluate alternative shipping fuels based on renewable energy sources. These were the renewable alternative fuels assessed by us according to the Brazilian trade reality, fleet and routes. The first group composed of almost, if not completely, drop-in fuels derived from biomass feedstocks and routes that produce or co-produce distillates. They are distillates. I understand that biodiesel has stability problems. I understand that SVO, straight vegetable oil, has viscosity problems, but they are more compatible with the existing motorization of the Brazilian fleet. And even they can be blended to the diesel used in the 4-stroke auxiliary motors. So they are mostly drop-in. They are not full drop-in fuels, but they are more compatible with the case of the Brazilian fleet and the long distance route of the shipping of the deep sea shipping in Brazil. The second group is composed of fuels from biomass feedstocks that require more severe adjustment in logistics, bunkering, storage, in shipping, and in harbors, and also severe adjustments in the motorization of the ship to be used. We are talking about biomass-derived liquefied natural gas, biomass-derived methanol, and bioethanol. This is the ethanol from Brazil. Finally, a third group composed of green hydrogen from electrolysis driven by PV, hydrogen carriers, being it ammonia or methanol, or e-fuels that require a chemical synthesis with CO2 from DACs. Please note that in our integrated assessment model, in the case of the Brazilian integrated assessment model, or in the case of our world integrated assessment model, CO2 might come from DACs, direct air capture, or from CCS, CO2 capture. And also the electrolysis might be driven by other renewable sources. But here we are going to assess the case of e-fuels from DACs and from PV. But in the third stage, we are going to assess also other possibilities in our integrated assessment model. These were the indicators and criteria used to compare the fuels according to the physical, chemical properties, feedstock availability, impacts, technological readiness, and so on. All indicators followed the Brazilian reality when suitable and were normalized to be used by a multi-criteria analysis. That's important. This is the Brazilian reality. I do understand that for other cases, for sea transportation related to shorter distance, or for other type of goods that are being transported by ships, perhaps the situation is different, but we are focusing our study on the Brazilian type of trade. So for instance, this is one type of analysis made for comparison. For example, clearly this is a static evaluation that does not consider the energy system as a whole. This will be done by our integrated assessment model in the third stage. This cannot consider externalities on water, land use, and so on. So this is the private price, the private cost of these fuels. And these do not consider learning curves and pioneer contingent costs for some options. We are going to do that in the third stage of the study. Please also note that usually, this is important too, the price of the bunker fuels, the price of the fossil bunker fuel. Bunker fuels are mostly made from liquid residuals from petroleum refineries, blended with different proportion of low quality gas oil. So bunker fuels for the reality of the fossil fuel industry, for the reality of the petroleum refineries, means non-premium premium fuels. They are byproducts of the truly campaign of refineries. So therefore, a major challenge here is the fact that an alternative fuel must consider that no refinery, no petroleum refinery runs for outputting bunker, but refineries run for output petrol, gasoline, diesel, jet, or depending on its hardware, lube oils, petrochemicals, and those derivatives are all high-pressed oil products. That's not the case of bunker fuels. This is another application of the indicators now showing the demand for space in the ship because of different energy intensities. So these are the kind of indicators that we used in the multi-criteria analysis, normalized in the multi-criteria analysis in order to assess and to compare the suitability of renewable derived bunkers, alternative bunkers, for the case of Brazil. As you see, the space required for hydrogen or ammonia and a hydrogen carrier are much larger than the case of the fossil fuel or even the bio-derived fuels. Another indicator which shows issues related to safety. For instance, let's see, we have always operational challenge when using fuels. We have our standard, which is the fossil fuel, and we have different challenge when we use other fuels. In the case of ammonia, let's see the case of ammonia. Ammonia is a kind of key fuel for some analysis. We have some challenges related to ammonia. For instance, in the case of ammonia, issues associated with toxicity and even spills to water are important. Ammonia, when it's spilled to water, forms ammonium hydroxide. And this ammonium hydroxide is very, very toxic for ecosystems. So we can control that, we can handle that, but there are some safety concerns of using some types of alternative fuels. Finally, the following shots. I'm going too fast, but because we have here two types of presentation for the first product and for the second product, as I said before, I made a very detailed presentation on this subject in April, and the report and also the executive summary in English are available for you if you ask, for example, iCS or Lavinia. So I'm passing fastly in order to have time to the second part of this presentation and also to the questions after then. Finally, we can see the charts. And here, for example, we highlighted some points for the case of SVO, straight vegetable oil. Important to say that for all vegetable oil derived bunker fuels, SVO, HVO, biodiesel, land use change uncertainties must be highlighted. But indeed, those uncertainties, particularly when associated with land use change, and more important, when associated with indirect land use change, can only be quantified, can only be, let's say, properly quantified with a land use model, or better, with an energy land use model, that case of integrated assessment models that can quantify land use system and energy systems. This will be done by us. So the case of the indirect land use change, it's very important. It's very important for the vegetable oil derived biofuels, but the indirect land use change cannot be seen without a proper model. And we are going to do that. Our global and our Brazilian integrated assessment models detail land use change in the world for the case of the global, and for Brazil in the case of the national integrated assessment model, and have more than 12,000 technologies, energy conversion technologies, including bio and e-fuels production rules. Other thing important too, interestingly, some of these rules, some of these biofuel production rules might output bunker, but they were not detailed here, since their focus are on high-grade fuels. So we are focusing our first and second stage products of our project with iCS on dedicated rules for bunker. But in the case of our integrated assessment model, we have some technological pathways that can output bunker, but actually they are focused on more varied fuels. For example, the case of alcohol to jet production pathway. This is a pathway to produce jet fuel, a high-grade fuel. But by producing jet, it also produces residual oil that can be blended or that can be converted to bunker fuels. So now the case of the biodiesel, again, almost drop-in fuel. It's not a full drop-in biofuel, but has a lot of challenges to be used because we are now blending biofuel, biodiesel into diesel. And we know that we have competition with other use. We have land use change uncertainties. We should be always aware that food energy competition can establish a cap for oilseed use, which is both physical and economical. And in the case of biodiesel, we have also the problem related to chemical and thermal stability. Then the case of HVO, which is a hydrotreated vegetable oil. So it's better than the biodiesel, it's better than the SVO. Brazil has some experience in producing this type of fuel, not for bunker, but for diesel. It's the case of H-Bio that was produced by Petrobras in some oil refineries. But again, land use change uncertainties, that's LUC in our short, matters. So matters again, always the case for the oil seeds. Then the hydrotreated pyrolysis oil, whose major issue is still lower technological readiness level. It's not a mature technology. It is a promising option given the possibility of processing residues and the quality of the fuel after hydrogenation, but is still a very costly route and not fully developed technological route. In the case of the Fischer-Tropsch diesel, the FT diesel, whose major advantage is the quality of all fuels, including bunker, that can be co-produced by this facility. So this is a facility that can produce diesel, but will also produce naphtha, LPG, and also some residual oils that can be blended to produce the bunker fuel. It can also be based on residues from biomass. So the impacts on land use change of this technological pathway are smaller, if null. But it is still costly and not yet completely mature route. Is more mature than the previous case, but it's not yet completely mature because of the gasification of the biomass. The gasification of the biomass is different from the gasification of coal and petroleum residues, and therefore we need still to achieve the commercial stage of this route. But we have some demonstration plants, the case, for example, of Total plants for production, for example, for the production of, for example, jet fuels from eucalyptus. Now, bio-LNG, so this is the methane, liquefied methane produced from biomass. In this analysis, we focused on LNG from biodigesters and also considered the issue of methane leak. And in our IAM, in our integrated assessment models, there are other sources of renewable LNG. Worth to say that we have before studied the case of LNG, fossil LNG, in Brazil's cabotage. But now we are focused on international shipping, not the cabotage. Given we have possibilities for using LNG in cabotage, but for the international ship, in the case of Brazil, there are a lot of challenges related to retrofit, bunkering, logistics, storage, especially, again, for the type of deep sea shipping in Brazil. Some of these holds for methanol, but methanol has a main advantage because of its liquid state under standard conditions. Methanol is a liquid on the CNTPs, which solves many of the logistics challenges faced by LNG. Methanol can be also produced from various sources and routes, and it's a consolidated chemical product. It's a consolidated industry. It's a very mature industry. There are some problems related to the flash point and the toxicity of methanol, but there are already procedures to deal with these problems. Again, now the ethanol from sugarcane, because we are talking about the case of Brazil, there are also the possibility in Brazil to produce ethanol from second generation fuels and also from other sources besides sugarcane. But we have challenge here because of the needed adaptation of the ships to use ethanol. And we all have to be aware again for the fact that ethanol prices in Brazil and also in the world follow gasoline prices. And gasoline is a premium petroleum product. Gasoline has a premium price compared to the Brent, for example, and by that has a very higher Brent premium price when compared to bunker fuels. But if I have time, perhaps I can talk later about some important possibilities, technological possibilities to use ethanol in the case of ships in Brazil, and how the Brazilian science can contribute to that. We are in a frontier area to process ethanol in fuel cells in Brazil and to use it in ships in Brazil. So we have some possibilities here, but not for the short term and perhaps not for the international deep sea transportation. Then the hydrogen, the green hydrogen. This is not the hydrogen from fossil fuels, which is the major part of the hydrogen produced as of today. More than 97% of the hydrogen comes from fossil fuels in the world, but has many issues. Inflammability, density, diabatic flame temperature, corrosion by embrittlement, and for hydrogen production from electrolysis, we need fresh water, electricity, and space. I will wait for Johanna to detail that for you. Johanna will show you later the needed space and water for producing hydrogen. Ammonia, green ammonia. So this is the ammonia that derives from the hydrogen, which is green. Ammonia from hydrogen from electrolysis. I'd like to add to this shot the important retrofit requirements of the existing fleet to use ammonia. Ammonia is much better than hydrogen, of course, and that's why I think some reports and some important reports, some very good reports, are betting their choice in ammonia, but it's a low density fuel which is not directly, that cannot be directly used by internal combustion engines or fuel cells. We must crack ammonia before using it in these conversion technologies. If we talk about new ships based on fuel cells running with ammonia, requirements are huge, including the need for pre-cracking ammonia, as I've said before. Perhaps for fuel cells, if you want to use fuel cells in Brazil in shipping, Brazil should focus on ethanol direct fuel cells, not on ammonia, but on ethanol. Actually, our School of Engineering, COPPE, my School of Engineering, COPPE, is at the scientific frontier in developing this option, the direct fuel cell running with ethanol. And we plan, our school plan, to test it in the next decades in boats. But again, this is not the case for large ship transportation, for low value added goods, for large distance transportation in the short term. Perhaps in the medium to the long term, this could be very suitable to Brazil, also because perhaps the electricity-driven urban mobility will challenge the use of ethanol in private cars. And then we are going to have ethanol for other uses, and perhaps a good use for ethanol is to be used in fuel cells, in ships, or in trucks, so on. So that's the case of, that's the first e-fuel. This is a liquid fuel, completely full drop-in with high quality. Here we focused on DAX, so the CO2 comes from direct air capture because of the expectations about this possibility in other scientific reports. For example, a report that was launched this year by the expert shipping group from the UCL focused on PV-driven electrolysis plus DAX. And they bet a lot on this possibility. That's the same case of the sky scenario of Shell. That's why we wanted to have a highlight on our analysis on this possibility. But again, our integrated assessment model can have other sources of CO2. For example, CO2 from ethanol production, CO2 from fuel gas from combustion. And we also have other possibilities to drive the electrolysis, not only the PV sources. But here we wanted to evaluate the impressive requirements of water, area, chemical input, hydroxide of sodium with chlorine co-production, for example, needed by this route. This is not usually highlighted in other studies. And I have to make an exception for a recent paper published by Rio Montt, the first author of this paper. But actually, I can see many papers talking about the chemical input required by DAC plus F-fuels route. Again, we have an electric fuel here. This is the natural gas, the methane produced from electrolysis. This is not the methane from biomass, but from electrolysis of water using PV-driven electrolyzers. That's the case of methanol. In terms of the fuel, the properties of the fuel is the same properties, no matter if it comes from hydrogen or it comes from biomass. But actually, this is mostly a very expensive route, electricity-driven route. Then we have the criteria for the analysis. These were our criteria. And at the end, we agreed with Lavinia and the iCS that we have to give more weight for the global sustainability. Let's say that's the focus of this study. So this is the focus of this study and not for all studies. If we have to focus on the technology, perhaps we are going to give more weight for applicability. If the focus were on costs, so the case will be to give more weights to economic. But our focus here, again, is the draconian targets of the IMO for 2050. So the major issue is the CO2 reduction related to these fuels. And then the technical applicability, the availability of the fuel for reaching this goal. And then we reached 5 fuels to be detailed in the second stage of our study. But please remember that all of these fuels are inserted in our integrated assessment model. Not only the 5 ones that will be detailed by Johanna, but also the other fuels and other possibilities for the production of liquid fuels to be used in ships. Let's say the Oscar goes to these 5 possibilities here. FT diesel, because of the quality and the full drop-in feature of this possibility, and is a quite near, is close to the maturity. I can say that technically it's almost mature. The problem here is the cost. HVO, we have the land use change concerns about this possibility, but we are going to see that in our integrated assessment model. I do acknowledge that we have problem here because of fuel energy food competition, but we have to see that in land use models in order to understand if this is a bigger problem for Brazil. SVO, it's an available possibility, mostly I think to be blended to the bunker, not to be used completely as the fuel in ships. E-diesel, a cost possibility, but a full drop-in possibility, and is an electro fuel, so it's a possibility too. And in our integrated assessment model, I think we have low-cost sources of CO2. For example, CO2 from ethanol, from the ethanol production in the alcohol fermentation. This is a very low cost of CO2. Perhaps this could be a good situation. And the biomethanol, because of the bunkering advantage of this technology, and because of the fact that we have already dual fuel motors that are being produced and are used with methanol and bunker and fossil fuel bunker as the pilot of these motors. So we have already the established industry of dual fuel motors with biomethanol. We have methanol storage in many harbors in the world, in the largest harbors in the world. This is a consolidated route. So this is a possibility. I think that's why the score of this route is good, and which indeed was selected. So Joanna, now the floor is yours. Thank you all, and I will leave the floor for Joanna.
Well, thank you, Alexandre. Thank you, everyone. May I be able to share my screen?
I think you are. And I just have to say that we actually a bit short on time, so I'll ask you, Joanna, if you could do your presentation within the next 15 minutes.
Yeah, I'll do my best. But
okay.
Before that, Alexandre needs to stop sharing his screen so I'm able to share mine.
Yeah, I'm trying to do that. Sorry. I have some troubles here. Okay.
All right.
All right.
Yeah.
Yeah. Can you see my screen now?
Yes. Yes.
Perfect. I can't see you because I'm in a PowerPoint mode. But yeah, I hope it will work if I just go through. So can you hear me well?
Yes.
Perfect. So I'll start 15 minutes sharp. I'll do my best. So in my second part, and this is me, I would like to share with you preliminary results we got from the second stage of our project, meaning evaluating the technical potential for the 5 selected fuel routes aligned with a life cycle assessment to evaluate greenhouse gases from the entire cycle of the fuels. So those are the steps we took in our georeferential analysis. We start by modeling the required feedstocks, and in my next slide, I will detail which feedstocks were considered, and we identify the production hotspots, meaning the areas with a higher density and higher, the greatest potential for feedstocks. And once we did it, we cross-checked the availability. Sorry, just having some troubles passing the slides. Okay. And then we cross-check our potential and we compare it with the current bunker fuel consumption, and we overlap layers to evaluate the distance from the production feedstock potential, the so-called hotspots, with the distance to maritime terminals. And we evaluate the logistic challenge. And we considered 4 major ports to do so, as I will show in the next slides, where we have detailed maps for it. So these are the feedstocks we consider for the 5 evaluated fuels. For straight vegetable oils and hydrated vegetable oils, we considered mainly oily crops, the ones with a higher potential and availability in the country. And I would like to highlight the given technical potential that we consider we are not evaluating eventual competition with other end-use fuels. That will be done in the third stage of our project when we integrate the evaluated and select routes with integrated assessment model. So just a caveat, the potential we are given is not, how to say, the realistic potential, it's merely the technical potential, so far from being the feasible one. So for the Fischer-Tropsch diesel, we consider mainly lignocellulosic materials from agricultural residues, once again considering major crops in the country, sugarcane, soybean, corn, wheat, as well as eucalyptus and pinus and residues from forest extraction. As for the biomethanol, we consider an aerobic digestion route, and we considered mainly manure, municipal solid waste, sludge, as well as other agricultural residues, considering rice straw, which is an important crop in the southern part of the country, soybean crops, corn, and wheat, and vinasse, which is a liquid waste or a liquid co-product from the sugarcane industry to produce ethanol. Lastly, for the electrodiesel, as earlier detailed by Alexandre, we consider constraints from solar radiation, water availability to produce hydrogen from electrolysis, and the solvents needed for the direct air capture process. As we are running short of time, I will leave this as it is, and if there is further questions, I'm available to answer that in the Q&A session. So, yeah, no, sorry. So here in this figure, I hope you can see the technical potential. And we cross-check it with the total demand of bunker in Brazilian ports in 2018. And as you can see, except for electrodiesel, which I'll detail later, all the other 4 routes present a high technical potential, actually much higher than the average fuel oil outputs and the consumption in Brazilian ports. Once again, with the caveat, we are not considering competition with other feedstock uses for more mature or even more cost competitive routes, such as biodiesel, for instance, for road transportation. So in the next slides, I would like to share with you the hotspots location developed by our georeferential analysis and highlight some of the constraints we identify. So for straight vegetable oil and hydrated vegetable oil, I merged 2 maps because we are evaluating the same feedstock for producing different routes of fuels. And I would like to highlight that 80% of the feedstock comes actually from soybean oil. And as you can see in the map, the hotspots are mainly in mid-central region in the country, which, as I will show here, are quite distant from the major ports evaluated, actually 1,000 kilometers away. So we highlight and we raise significant logistic challenge and actually cost effectiveness of producing renewable-based shipping fuels 1,000 of kilometers away from the terminals. Would it be possible? Would it be sustainable? Would it be cost effective? It's something that we will actually evaluate in the third stage of the project, where we can already foresee some challenges here. So as for the Fischer-Tropsch diesel hotspots, we identified 2 major hotspots. One from sugarcane and soybeans in southeast and southern part of the country, which are actually closer to harbors, but an important one, again, in mid-central region in the country. And as I earlier mentioned, these hotspots faced a similar challenge showed previously, which means they are 1,000 kilometers away from the harbors. But we see significant potential, or at least the hotspots are much closer to the harbors in south and southeast regions. For instance, in Paranaguá and Santos and Ilha do Sal terminal, which actually could become a competitive advantage of Fischer-Tropsch routes. As for biomethanol hotspots, we merge and we evaluate 5 different hotspots in different states, starting from São Paulo in southeast region, and in the south, Santa Catarina, which with significant potential, but once again, we see higher potential for producing biomethanol from waste and sludge, comes once again from mid-central parts of the country. So for this reason, we evaluate and we foresee a higher competition in terms of logistics, at least the ones in south and southeast region in the country. Lastly, the electrodiesel hotspots. If you remember in my earlier slides, the potential for production is much lower than other fuels evaluated, merely 6,000 terajoule per year, compared with much higher from other fuels. But there's the advantages. Oh, sorry, I forgot to mention the hotspots evaluated. They were selected given how close they are with plants that produce the solvents needed for direct air capture. And also, as I mentioned, water availability, as I'll show later, and land availability. So although the electrodiesel hotspot actually presents a lower technical potential than previous fuels, those are close to terminals, which could eventually become an advantage in terms of logistics. However, electrodiesel production actually demands too much water needed for hydrogen electrolysis, which, if we can see here in this figure, the comparison of water consumption per terajoule of fuel produced. We compare biodiesel, petrol extraction, and natural gas, and is actually 10 times higher than others, than biodiesel becoming one of the benchmarks and the reference. So although we are not talking about drinkable water, this surely becomes a constraint, especially if we consider climate change and future extreme events that may become more frequent and actually more intense than the ones we see nowadays, eventually. As for land, it may also be a constraint if we think we need 10 square kilometers, which is around 4,300 square meters per terajoule of fuel. And that's actually 10 times higher than, for instance, an ethanol distillery. And that becomes the major, I would say 90% of the needed area comes from PV solar panels required for the plant and supply energy to the plant. So that also may be considered a constraint if we imagine we need about 1,000 football fields just to have one plant for electrodiesel. So if to sum up, just to summarize what I just mentioned, while Brazilian technical potential to produce renewable-based fuels is actually quite high and higher than the current consumption of fuel in Brazilian ports, we can't forget and we need to stress the logistic challenge that this may entail and how we can overcome it in the future. So in the last part of my presentation, if time still allows, if Lavinia just gives me 5 minutes longer. I would like to summarize the life cycle assessment results we got from greenhouse gases emissions. I hope it's okay, Lavinia.
Yeah, sure. Of course I will. Yeah.
Okay, thank you. So to evaluate the greenhouse gases emissions, we adopt a life cycle methodology, which accounts for emissions and the process, not only in the so-called pump to hull, as you can see highlighted in green on the right side of the screen, but also the upstream emissions from producing the feedstock in farming, which includes fertilizers, other energy inputs, the fuel needed for transportation from the farming area to the processing unit, the fuel production, and the transportation to the port, which in some cases, as we've seen earlier, actually entails thousands of kilometers. And we also include, in the case of the electrofuel, the electrodiesel, the chemical industry, and the solvents required to synthesize the fuel. So the upstream process are so-called well-to-pump, as highlighted in blue on the left-hand side, and the pump to hull includes the combustion and the combustion of the fuel in the shipping. So the overall assessment is the so-called well to hull. So to run the life cycle assessments, we adapt a software available and developed by Neural in the US, so-called GRID. And to do so, we actually tailored significant inputs to ensure we were reflecting Brazilian realities and our case study assumptions. So we assume the functional unit being 1 megajoule of fuel produced. And we consider for this specific case study only greenhouse gas emissions, assuming the global warming potential of 100 years as defined in the IPCC Assessment Report 5, meaning we are assuming methane had a 28 higher warming potential than carbon dioxide, CO2, and 265 for N2O. The transport distance, quite large in some cases, were taken from the georeferential analysis, as I just showed in an earlier stage. And for the case of biomethanol, which is mainly produced from municipal solid waste and other sludge, we applied 2 different life cycle assessment methods. We considered a attributional LCA, which actually means we are allocating energy and emissions based on the energy contents of the product. And this is the most used LCA method applied for European Union biofuel and sustainable directives, because it's easier to compare one case study in one certain region from others. But given that we were actually reducing emissions and costs from solid waste that would be used to produce the biomethanol, we also assume and we expand our boundaries, assuming a consequential analysis, meaning what would be the avoided emissions from residue and wastes. So let's go through. The specific assumptions assume a mix and a merge from the different feedstocks considered in the hotspots identified, as earlier showed. So for straight vegetable oil, we considered 80% would come from soybeans. And here I would like to highlight that we consider only direct land use changes. And at this stage, second stage of the project, we disconsidered indirect land use, not because it is irrelevant, actually it's very relevant, but because on the third stage of the project, we actually have the tools to assess indirect and second order impacts from the fuels produced when we run our land use and integrate assessment model. So for a hydrated vegetable oil, we considered soybean oil again, which this two routes actually compete for the same feedstock, and we considered only renewable hydrogen production from electrolysis from renewable energies, solar PV mainly. For Fischer-Tropsch, we consider a mix of agricultural residues and forest residues. At the mix, branch has evaluated in the georeferential analysis. Similar for biomethanol, again, a mix of agricultural residues, vinasse, municipal solid waste, and sewage. And for the electric diesel, we consider renewable based hydrogen together with carbon dioxide captured by direct air capture units. So as we can see here, we compare our final greenhouse gases emissions from the entire life cycle with conventional and fossil fuels, and we see a significant decline of emissions ranging from 60 to 80%, depends on the case, on the fuel evaluated. So overall, our select renewable based routes are less carbon intensive than conventional fossil fuels. Among the green options we evaluate, Fischer-Tropsch diesel comes with the lowest greenhouse gas emission, and this is mainly because we are considering agricultural residues as feedstock. And given that I do not know any farmer that grows sugarcane for the straw or soybean for the straw, those emissions are much lower because they are being allocated to the major crop rather than the residues, meaning that emissions only account for transportation and fuel processing. I would also like to highlight for the case of biomethanol, we have a higher range, so a higher uncertainty of the results, and this is mainly due to the wide range of feedstocks we are considering, ranging from agricultural residues, as you've seen earlier, as well as municipal solid waste and other sludge. So if we consider and if we account for avoided emissions from residues, assuming consequential life cycle assessment approach, as you can see in the green bar in both figures for Fischer-Tropsch diesel and biomethanol, we can actually have even higher savings of emissions because we are avoiding the treatment from those residues, and also because we are avoiding methane emissions released in open air bumping waste or landfills, or N2O left when we have agricultural residues left on the field. So just my last slide on life cycle assessment. I promise, Lavina. I would like to highlight the major difference why Fischer-Tropsch diesel and electrodiesel actually have such a large difference in greenhouse gas emissions. So we see for Fischer-Tropsch process, we have the lowest range of greenhouse gas emissions, accounting for only 4 grams per megajoule, while for electrodiesel, we have 32 grams per megajoule. And this is mainly, as I mentioned, due to the solvents and the required energy for the direct air capture process that actually relies on natural gas combustion. And while natural gas is less carbon intensive than other fossil fuels, it's still nonetheless a fossil fuel. And when compared with renewable energies, this is the main reason why we have this difference. So I'm over with the life cycle, and I would just like to share with you our take-home message, and then we go straight to Q&A and the debate. So we showed in our first and second stage of our research project that Brazil actually presents significant advantages to produce low-emission alternative fuels for the shipping transport. And actually, it shows significant reductions on greenhouse gases emissions which could support IMO target for climate change mitigation by reducing 50% of emissions. Nonetheless, we can't forget about logistic challenge, especially when we consider feedstock hotspots in the mid-center region of the country, which is 1,000 kilometers away from the coastline and the terminals. So this actually entails a logistic challenge, lack of infrastructure in the rural areas of the country, which are associated with higher greenhouse gas emissions, as well as higher costs. We only evaluate 4 terminals, and actually we could consider other ports, which could eventually reduce the distance, but at this stage we consider only the major ports in the country. As for electrofuels, we see a lower potential, but actually those plants that produce the solvent required for direct air capture are close to the coast, which could actually be a logistic advantage and competitiveness, but we can't forget the water required and also the land availability in those regions. So this is my last slide. Just to highlight, as previously mentioned by Lavinia and my colleague Alexandre, this is a 3-step project. We just completed the second phases, where we developed the georeferential and life cycle assessment analysis. And in the third stage, we will develop an economic assessment and run our integrated assessment model, where we can actually see the potential and competitiveness of this select fuel routes compared with the entire energy system. So we are due to complete this last stage in July, and very likely we are having a final webinar. So we are counting on you if you are curious to see the final results of our study. So thank you very much, and apologies for running a bit over. And I hand it to you, Lavina.
Thank you, Johanna. I have to say that it's very hard for me to be, minding the time, and I apologize to you guys for that. I have to be, mindful of the time, and I wish we had more time to discuss, more in depth the presentation. So thank you, Guy, and sorry to be keeping, reminding you of the time. But I would like now to turn to Yarong Zhao. She will be commenting on the presentation and on several points she found interesting. So I ask you, Yarong, are you able to unmute your phone?
Oh, yes, I am.
Okay, so you have now about 10 minutes to provide your comments. Thank you so much for participating.
Sure, no problem. That's my pleasure. And thanks for having me at the webinar. And it's a really great study with a very comprehensive analysis. And I am also very glad to see that Brazil is making the efforts to contribute to decarbonization in the shipping sector using science-based information. And maybe just a bit background about ICCT. So ICCT is an independent NGO looking into practices to address air pollution and the GHG emissions from the transportation sector. And we have office in multiple countries, and I'm currently based in the US. And I'm with the fields team at ICCT, and our team is working on identifying the fields that can offer the greatest carbon reductions based on life cycle analysis. And we also work closely with policymakers on the design and implementation of effective low carbon fuel policies. So regarding today's presentation, I have 3 main comments. And the first one is on the indirect land use change impacts of biofuels. So I believe like many of you already know this, but I just want to readdress a little bit. So biofuel has direct and indirect land use change impacts, which can cause GHG emissions from disturbing carbon stock in the biomass and also in the soil. So direct land use change is pretty straightforward. So it's basically the conversion of natural land, such as forest, to the production of biofuel feedstocks. But indirect land use change, or we call it ILUC, is a bit more complicated, and it's particularly an issue for food and feed crops that have high economic values. So for example, if soybean is diverted from food to make biofuel, then the crop price would go up, and farmers all over the world would respond to the price increase, and they would consequently clear more natural land to grow crops in order to maintain the food supply and demand balance. So depending on the types of feedstock, the magnitude of ILUC emissions could be substantial. And multiple studies have shown that certain food-based biofuels cannot really deliver carbon savings, and some may even have higher carbon intensity than the fossil fuels. So just to give you an idea, so there's a global model, integrated assessment model. They estimate that soybean oil in Brazil actually has an ILUC emission of more than 100 gram GHG emissions per megajoule of the fuel. So this means that the ILUC emission of soybean oil itself is already comparable to the total GHG emission of the fossil fuel. So given that ILUC is such a big deal, multiple biofuel policies, for example, in the EU and also in the US, have already factored it into their policy design. And it's not just the national policies. The aviation sector also includes ILUC in its carbon offsetting and reduction scheme known as CORSIA under the International Civil Aviation Organization. So right now, it's not clear yet in terms of how IMO is going to design its carbon policy, but it is likely that it might just follow the existing fuel policies and would include ILUC in terms of accounting for the carbon intensities of the fuels to meet their target. So I guess what I'm trying to say here is that in order to understand the true carbon decarbonization potential of biofuels, it is really essential to include ILUC emissions when estimating the carbon intensities. And I hope the audience here today don't walk away with a wrong perception from the presentation and think that, oh, there is a huge carbon reduction potential from all types of biofuels, even from those are food-based, because the results here are only a part of the story, and the inclusion of ILUC emission would change the results significantly. And I know that the research team is going to do the ILUC analysis in their next phase, and that is great. And I'm really looking forward to see the final results, and hopefully by that time, it could provide some true implications on the fuels that are really able to help decarbonization, but exclude the ones that are not as sustainable. So the other comment I have is regarding the scale up of sustainable feedstocks and the advanced fuel pathways. So as I just mentioned, food-based biofuels generally do not really bring climate benefits, but unfortunately, so far the progress on alternative fuels for the transportation sector has been dominated by those conventional biofuels from food crops, because it's really cheap and it's also easy to make. But in contrary, there has been very limited progress on advanced fuels using sustainable feedstocks. And those fuels usually can provide deep carbon savings, like the FT diesel made from agricultural residue that is just shown in the presentation today. And currently, there are very few facilities around the world are producing advanced fuels, because it's very expensive and it requires substantial upfront investment. So we need to, we really need to come up with some effective measures to scale up these low carbon advanced fuels, and actions really need to be taken now to allow the time for learning curve. And to do this, it would require some sort of policy support, such as financing schemes and also volumetric mandates for advanced fuels. And it is also important to demonstrate some long-term policy certainty to the fuel industry. And such long-term certainty can actually help to reduce the investment risk and also attract investors. So in the next phase of the study, I know the researchers are going to look into the economics of the alternative fuels as well. And I think it would be also helpful not only to have the cost analysis, but also to provide some recommendations on how to overcome the cost barriers and to really help to scale up the low carbon advanced fuels so that they can in reality be produced and be used to decarbonize the shipping sector. And last is that I see there are some discussions from the chat regarding the IMO decarbonization target. And I want to comment a little bit on that. So the transportation sector, including the shipping sector, it's kind of like an exception in the global decarbonization efforts. Many of the other sectors, they are already showing some reduced GHG emissions, but that is not the case for the transportation or the shipping sector because its emission is increasing over time. So it is really crucial to have the decarbonization targets in place, and the sector has to take actions in meeting those targets. So I think in the past, the shipping sector has made some progress on improving its energy efficiency, but studies have shown that efficiency alone is insufficient to have deep decarbonization. So that is why we have to find low carbon alternative fuels as an addition to improving energy efficiency to meet the decarbonization target. And that also speaks back to my previous point on identifying and scaling up the advanced fuels that will have true carbon saving potentials. So yeah, so that's my 2 cents, and happy to listen to the Q&A now.
Oh, okay, so thank you so much. So we got here, a few comments on indirect land use, and I'll have Alexandre or Johanna comment on that, but a few comments on indirect land use, which I think it's really important in the case of biofuels for Brazil, especially because most of the impact we could see here in Brazil will come from indirect land use. So the point is, results are not final, and when they include the indirect land use assessment, we might see a different picture. That's what I got from the presentation as well. The other thing on cost analysis, and not only the cost analysis, but how to overcome the cost barriers to produce the fuels. And regarding the very active discussions on the chat about the IMO targets, I think it's something we could discuss, and it is being discussed in the chat, but I have to just mention that the targets are there. We have to comply with the targets. I think probably the most productive discussion, and agreeing with my colleagues who are discussing that, is to see how we can actually achieve the decarbonization targets. So with that, I open to questions, and I have to say that we have a very active chat. So most of the questions asked have already been answered. But I have one question that has not been answered, and I'll ask this question, and then I turn back to Alexandre and Johanna just to comment, to make final comments and to answer this question. And the question was made in the beginning of the presentation, so was in the first part of the presentation done by Alexandre, and the question is, the energy spent on board for management and fuel safety reasons could be counted for efficiency. That is the question from Fernando. So with that, unless you guys, and I encourage you to send more questions if you have, I would probably turn back to Alexandre and Johanna to comment on what our colleague Jeroen has commented. And then if maybe you could answer this question as well. So Alexandre and Johanna.
Perhaps I can start. I will start with this question. Yes, we are accounting the energy needed for the operation of fuels inside the ships. So these include the case of safety. For example, in the case of methanol, to handle methanol because of the toxicity, we spend a little bit energy for that compared to the bunker. So all the bunkering situation inside the ship and inside the harbor is accounted and will be accounted in our analysis. And this will, of course, affect the fuel consumption in the ship. So this is accounted in our analysis. In the case of the ISO comments, I fully agree with her, and thank you for this comment. But actually, we have to understand that, as I told in my presentation, I think biofuels has a major challenge because of food energy competition, because of land use change, and the major importance and the more complex situation is related to ILUC, to the indirect land use change. But actually, the only way to see that is by running land use models. We have to run a land use model to see that. For example, the case of soybean in Brazil, and I think some colleagues of myself can complement on that. Brazil now produces soy to export raw soy to China. Basically, most of the Brazilian production of soy is to the exports to China raw soy. And the soybean oil is not the main product, it's just a co-product. So depending on the way you see the land use change, you can see that soy is the major factor behind the deforestation and other things, or the soybean oil. So we need a land use model to see that. And for another thing, in the case of the biofuel facilities, as I said, I think that we have to have biofuel facilities co-producing different fuels, not producing only one fuel. And interesting, perhaps the IMO target and the IATA targets, the targets for the aviation sector, can co-produce interesting results. If you have the model representing, depicting the whole energy system, not only the shipping system, we are going to see jet and bunker fuels being co-produced in the same facility. And that's a point that we are expecting in our simulations. And finally, I like the case of the e-fuels, but I think we have also to evaluate the demand for area, the demand for chemical inputs, and the demand for fresh water related to them. We see biofuels as a land use problem, but we forgot that a major problem in the world is fresh water availability. And we are proposing to scale up a route that consume water, that demand fresh water, and is based in high footprint plants, demand a lot of space. So can have also some indirect land use change too. And again, to see that, we need to have a land use model, not only for biomass, but also for electricity, for water consumption, and so on. That's our target as a group and the target of other scientific groups in the world. Thank you, Lavinia.
Can I just add one question, one very interesting question, and I'll say it's just a final question, and then I'll turn back to you, And Johanna, if she wants to make final comments, because we are just approaching the end of the webinar. But there's a question regarding, the question is the following. Considering that international shipping is a worldwide activity, what are the difficulties for the adoption of different low carbon fuels or solutions that fits local and regional context better? And I think this goes to biofuels as well as an option.
Thank you, Lavinia. I don't know if someone wants to add something, perhaps Joanna or other colleagues from the group. Actually, Lavinia, this is the thesis, the PhD thesis of one of the students, of one of the researchers of this group. It is Francielle. Francielle is now working on that because we are trying to understand this case, how to use different fuels, how to use different fuel logistics in the major routes, not only the case of Brazil. As I can say to you, for that in the short term, the best thing to do is to use drop-in fuels or almostly blended drop-in fuels. For example, we know that we can use 10% in volume of biodiesel or of oil, vegetable oils, or things like that, blended to bunker. This won't solve the target for the IMO, but it's possible to do that. And this can be done without major problems. But when we talk about major strategies, therefore, we have some problems. I think we have some problems. And perhaps I think there will be some regional strategies, for example, ammonia for some cabotage, ammonia for international shipping, but for example, perhaps in the Mediterranean Sea. But for these major routes of Brazil, I don't know, perhaps methanol, perhaps some fuels that have already facilities all over the world in harbors can be better. I don't know.
Okay.
Yeah, thank you, Alexandre. If I may just complete very quickly. Given Brazil particularities for long distance requires, which are very different from an European context, there's actually other alternatives that we are considering. And as Alexandre just mentioned, this is why eventual biofuels or biomass-based routes can become more competitive. With the caveat, as we show, there's logistic constraints that need to be overcome by that. And concerning your question, and as a final remark, currently shipping emissions are not accounted under the Paris Agreement goals. And that if we consider seriously mitigation targets for the entire economy and the entire world, because greenhouse gas emissions do not need visa or do not have passport and are a global concern that affects the planet all over, would be important in the next COP to be held next year, was cancelled or postponed this year due to the pandemic, to consider to include aviation and maritime transport sectors along with others. Otherwise, we may run or we may have the possibility of considering run emissions and split overs from one sector to another. Thank you.
Mm-hmm. Okay, so I think we conclude this webinar. So I'd like to thank all the presenters, Alexandre, Joanna, and the whole research team. I'd like to send my special thanks to Yaoran Joe, to ICCT for helping us in this debate and agreeing, participating. Thank you very much. We hope to continue to engage with you and exchange information. And thank you all the participants. And on behalf of Climate and Society Institute, I thank you all. And we will be sending you shortly the presentation, the recording of this webinar, and a consolidation of all the questions that haven't been answered with the answers to the questions. So I see some of the questions, some questions are popping up here. So don't worry, we will address that and send and answer and get back to you. So thank you very much and have a good day. Bye.
Thank you. Bye-bye.
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 Thank you, everyone.
Thanks,
Bye-bye.
Lavinia. Thanks, everyone. Bye-bye.
Thank you.
Thank you very much.